Well, the first thing is that if you look in the under the juniors tab on OneNote, I put in the equation sheet that I'm going to give you for the final. So as you're getting ready to make your notes for the final, it's probably good to keep this in mind, knowing what you've already got. I think I got everything in there. Yeah, I think I got it all. So that's your equation sheet. I also put blank copies of, this drives me crazy, blank copies of the tests, including a blank copy and key for chapters 14 and chapters 12. So if you wanted to fresh copies to study from or to do practice with or whatever, those are there. Everybody cool? Okay. Reminder again that your last problem set is this one for Sunday for chapters 14 and 12. All that information is on the board and on the end of year agenda and on My Notre Dame and in the grade book. I don't know how many more times they have to go by. It's not even that much grass there. I don't get it. And then that, in addition, remember you have 2 homework assignments get dropped. So if you have done everything up to this point, you don't really need to turn in the last one. Like I'll probably mark it as missing if you don't do it, but it won't actually affect your grade one way or the other. So don't lose your noodle if it's a particularly hectic weekend and you're like, yeah, I just didn't have time to get to this. Obviously, you should try to do those problems at some point because that stuff is going to be on the test. But you can just do it enough to where it's like, yeah, I got the idea. You know what I mean? You don't have to do every single one kind of thing. All righty. Any questions about any of that stuffs? Okay. Today, the very last thing that I'm going to be teaching you, we're going to do a quickie version of chapter 12. This won't even take the whole time. So, it just doesn't stop. They should contract an electric company that uses electric tools. All right. So what we're going to be talking about in chapter 12 is we're going to be talking about, using regression equations. So the general idea is you're going to start with some data set. And we're going to use our calculator to create some regression equation. And there's going to be 6 different types of regression equations that we're going to be responsible for. So there could be linear regression equations, God bless you, quadratic, cubic, exponential, logarithmic. Oh, what was that? I think it was written this way. Note that that's an ln. So every logarithmic that you're going to write is going to be a natural log. So there's 6 types of regressions that we'll worry about or be responsible for. The good news for you is the calculator is going to do all the construction for you. What you're going to be primarily concerned with is, which one should I pick? Right? So how do I choose which one of these 6 that I might want to use? Probably the most obvious way is to look at the scatter plot. So what's a scatter plot? Just like you're plotting the data like X's and Y's, right? So you're basically going to be looking at the shape of the data. What should a scatter plot look for, like for the linear? What are you looking for? Should look like a line? Oh yeah, sure. What is the shape for the quadratic? Yeah, that's called a parabola, that U shape. How about a cubic? That's kind of like 2 U's. For an exponential, you get that hyperbola shape. For a log, you'd get that kind of shape. And the power are really versatile. So like this can really vary. You can get stuff that can look like a square root function. You could get stuff that looks like a quadratic or a cubic or some other higher degree polynomial. You get all kinds of cuckoo fun stuff, but it's a pretty versatile function. Okay with that idea? Jackson, is that a hand? Sure. So let's take a look at an example. So here is a data set. I'm going to go through now how to do a bunch of stuff on your calculator. If you have your calculator with you and you're somebody that likes to follow along, I invite you to take your calculator out so you can follow along with me. If you're a sit and watcher, that's cool too, but if you need need a refresher, you can always come back to the video, to this part where we're going to go through on our calculator. And if you want to sit next to your friend that has their calculator and you don't, so you can look on with what they're doing, feel free to move around or whatever. Okie dokie. All right. So first thing I need to do is I need to type this data into my calculator. To do that, I'm going to press the Stat button, and I'm going to go to the Edit tab and select the Edit command. Now, you can see that I already have this data typed into my calculator. Probably most of you have nothing typed in as far as data goes. Although if you do have data, there's 2 ways to get rid of it. One way is you can press Delete to delete a single data point. Or if you have a whole bunch of data that you want to get rid of, you can move your cursor up onto the label. You can press Clear and the down button and it'll wipe the entire column for you. I'm just going to real quick here retype in that data that I just wiped out of there. What you don't want to do is when you move your cursor up onto the label that says L1 or whatever your label says, is press the delete button. Okay, that's just going to remove that list entirely. It's not going to get rid of the data. It's just going to remove the list from where it's at. It's kind of a pain in the butt to fix it after that. We can still fix it, and I can help you if you've done that. Are you laughing because you just did it yourself?
I was laughing because I hit the delete button, not knowing it was supposed to.
Yep. We can fix that in a minute, Mackenzie, but for now, just use the whatever list you have available to you. You'll have to update your names when we get to that point. But if you want some help getting that back, I can help you do that in just a few minutes. Okay, everybody following along, got your data typed in? All right, so that's how we enter data. Next step I'm going to want to do is look at the scatter plot for this data. I'm not going to do this by hand. Again, I'm going to have my calculator do this for me. To have your calculator create a scatter plot, you're going to press second and the y equals button. You can plot up to 3 scatter plots at once. I'm going to be using the plot 1 to plot this one. So first thing I want to do is select the on option so it displays my scatter plot. The first graph option is the scatter plot, so I'm going to select that. Now I typed the independent variable into L1 and the dependent variable into L2. So my X list should be L1 and my Y list should be L2. Now, if you had to use different lists because you were missing your L1 or you accidentally deleted it or something, Mackenzie, you'll notice in blue above the numbers 1, 2, 3, 4, 5, 6 is L1, L2, L3, L4, L5, L6. So if, for example, if I needed L3 here, I can just press second the number 3 and that'll get me L3. I don't need that because I didn't delete my L1. But if you did, you just change the names there for whatever names you had to use. Everybody cool? And the last option is just what the point looks like. So I like to use the squares because it's easiest to see. So that's what I'm going to use. Everybody good? Next thing I want to do is I want to press the zoom button. Actually, it's going to be a pain, so I'm going to exit out and then press the zoom button. And I'm going to scroll down and I'm going to look for the zoom stat option. I really strongly encourage you guys using this because now we don't have to think intelligently about the window. Your calculator is just going to look at the values that are in your X and Y's and use those values to set the X min, X max, Y min, Y max, and everything. So it's going to be real nice for me. Oops. I didn't mean for this stuff to be on. Okay. So here's my scatter plot. Everybody cool with what we're looking at? Did you guys get a similar picture on your machine? Excellent. So what shape does this look like? Oops, let me do this so we can look at them both at the same time. Okay, somebody says exponential. What else? Does anybody else have one that they think it looks like or disagree? Okay. So somebody else says log. Anybody else want to chime in here? Mr. Kulik thinks this looks a lot like a cubic also. So which one is who's right? Now, wouldn't it be nice if there was a way to tell beyond just like look at the picture and see which one seems like the best fit? There is. So we have 2 different measurements for telling how good of a fit our model is, or our regression equation again is. So we have two measurements for this. One is the correlation coefficient. This is abbreviated with the letter R. We use the correlation coefficient only for linear models. It's really only appropriate for linear models. And R exists on a continuum from -1 to +1. At 0, we have no linear relationship in the data. Now, 0 is kind of a theoretical value. I doubt in practice you'd ever see a data set that had 0 correlation. That would imply the data is like perfectly random across an infinite space. I'm not sure what that data set would look like there. At 1, that would mean that our data is perfectly linear and has a positive slope. When I say perfectly linear, that means that there exists a line that passes through every point in our data set. So I can construct a line that goes through every point in our data set. Not just some of them, not all but a few, but every single point in our data set could lie on a line. Everybody's cool with that idea? -1 is also perfectly linear. But it just with a negative slope. Everybody cool? Okay. So basically, as the absolute value of R gets closer to 1, the better the linear fit. Or we'll just say the more linear the data is. The other measuring tool we have is the coefficient of determination. And the symbol we use there is R squared. This goes 0 to 1. And basically what 1 means is that all the points on our data set so that would imply, if the value is 1, that all the points in our data set are points on the curve that our model represents, right? And 0 would just imply like no relationship. And I guess I would put no blank relationship. So like no quadratic relationship if we did a quadratic, or no cubic if we're talking about a cubic. So again, as R squared gets closer to 1, the better the model fits the data. Okay. So I haven't told you at all how to calculate these values for r or r squared. Why do you suppose I have neglected to do that? The calculator is going to do it for us. Righteous. So let's go back and look at that data set that we were just playing with. So what we're going to do is we're going to ask the calculator to create an exponential model, a logarithmic model, and a cubic model. And we're going to look at the r squared values and compare them and decide which one of these was the best choice. Everybody cool with that plan? So what I'm about to show you is how you create a regression equation on the calculator. In the act of creating that regression equation, we're going to also get the values for r or r squared, or I should say r squared. Okay? So I was looking at my scatter plot. I'm going to exit out of that. What I'm going to do now is I'm going to press the stat button again. But this time I'm going to go to the calculate menu. So I'm going to move over to the calculate tab. And if you scroll down, you're going to notice that after the first three options, the next options are all of my regression equations. So there's the linear regression, quadratic, cubic, quartic. There's another linear. I don't know why we need two of them. One where the A is the constant and the B is the coefficient. And another where the A is the coefficient and the B is the constant. Like whatever. I don't know. ln reg is our logarithmic regression. The log they're going to use in that is the natural log. Exponential reg, power reg, and then we have some others that you guys won't be responsible for using.
Cool. What did you press to get that menu?
Stat, and then I moved over to calc. You're welcome. Okay. So exponential was the first suggestion. So I'm going to select that. Now I typed in my independent variables into L1 and my dependent variable into L2. So I'm going to make sure that those are set as L1 and L2. The default is whatever you entered last. So probably most of us are defaulted there to L1 and L2. We're never going to have anything in the frequency list. So you can just leave that, always leave that blank when we're doing the regressions for this class. The option store regeq is going to be a useful one. We're going to actually take advantage of that. So what this option does is it allows us, the calculator, to save that equation somewhere. The natural place to save it is into one of the y equals slots. So I'm going to save this first one into y1. So remember, to get y1, we press vars. We go over to y-vars. We select from the function option the y1. And then I'll hit calculate. So what I care about for right now is the r squared value, so 0.9205. Now, how many of us that did this didn't get the r squared values? Oh man, is your calculator broken? No, we just need to turn an option on. So once we turn this option on, it should stay on unless your battery dies or you reset your calculator or whatever. But we're going to turn this option on. If you don't have your calculator with you or you're not following along with us, I would suggest that you pay attention now so that when you go home and you get your calculator out and go to do this, you remember how to do that. So to turn on this option, we're going to press, well, the easiest way to do it is to press second and then the number 0. This opens up the catalog. The catalog is just an alphabetical list of all of the options on our calculator. The option that we need to find is called diagnostic on. So rather than scrolling through all the A's and then all the B's and all the C's all the way down to the D's, you'll notice above some of the buttons are little letters in green. So if I press the button that has the little green letter above it, that skips me all the way down to the D's in the alphabet. And then I can just scroll till I find diagnostic on. Okay. Once you've done that, we're going to press enter to select it and press enter again to execute it. And then if you press second and enter twice, it'll recall that regression equation that we just did, and you can press enter again, and now your r's and r squared should be there. And they will continue to be there unless something tragic happens to your calculator and its memory gets reset or whatever. Did that work, my dudes? Some kind of affirmation or something would help here. It worked? Oh. Okay, it's getting there, you think? Okay, great. All right, let's do this for a logarithmic now, right? So we'll do stat, calc, and then I'll go down for pick the ln reg. Remember, ln is the natural log. That's what our logarithmic looks like. I'm going to still be using the same data set, but this time I'm going to store this into y2. And then I'll hit calculate again. Here the r squared value is 0.7704. That's kind of bad. So right now the exponential seems like the better of these two choices. Everybody cool with that? All right, one more to try. The cubic. So we'll press stat, over to calc. This time I'll pick the cubic reg. And again, I'm going to store this time into y3. And the r squared is 0.9905. Ooh, that's pretty good. Everybody feel okay there? So just to illustrate now, let's look at what these functions look like in comparison to our scatter plot, right? Just for grins. So the first option was our exponential. So I'm going to turn off the other two just by pressing enter on the equal sign so they're not highlighted. And then I'm going to graph the y1. So this is my exponential. So it looks like it does a pretty good job in the beginning, but not so much as good a job at the middle or at the very far end there. You guys see that? Let's see what the logarithmic looks like. That apparently wasn't a very good fit. Let's put that back to a regular line. So here's our logarithmic. And we can see right away that, yeah, that doesn't even appear to be kind of the right shape. So probably clearly not a very good fit. And then let's see the cubic one. That's a pretty nice fit between our datas, right? Everybody cool with kind of what the r squared is representing? Visually, you can kind of see it now. Ella.
How would you know when to check the power one? That one you said it
Yeah, do you want to do it? Let's do it. I don't know. We're just kind of talking about it. Let's see what the power one looks like. The cool thing about the power function is it kind of will work for anything. It may not always be the best, but it's usually not going to be very bad. So if you do that, we got 0.9687. And let's just look at the graph for that so you can kind of get a feel for what the shape looked like. So here's our power function. It was doing pretty good until the end. What it can't do really well is do like bends. But like if it's kind of like a wavy-ish, you know, or like something that looks a little exponential or a little quadratic, but not like totally those things, it can usually do a pretty good job on that kind of thing. Or if it's bending the other way, you know, whichever way you're bending, but it can't usually do more than one bend. Everybody cool with that? So again, you probably would be given some choices and asked which one is the best fit. Now, some of us might have been able to see just with our eyes that the cubic was going to be the best option, but when in doubt, just do all the regressions and look at the R-squared values. Okay. What's the possible disadvantage of just looking at the R-squared values? What's up? They could be close, sure. Okay, let me add a little bit of context. Right now, this data is just numbers, right? What if I told you the L is like the length of an organism, and the W of L is the weight for that organism? Does a cubic really seem like it would make sense? Would you expect at some point, like, here, let's do this real quick. Let's turn the cubic back on. And we'll just extend that window out a little bit. Would you expect the weights for the animals to start getting smaller as they got bigger? Doesn't seem like maybe that's a realistic model once you give it some kind of real world context, right? You guys kind of see that? Now it fits super good, the data that we have, but maybe is not very, you know, like long-term realistic. In that case, maybe like the power model might make a little bit more sense there. Oops, daisy. So again, just to illustrate kind of what's going on. Right, like that seems like that makes a little bit more sense about what's going on with our organisms. You see what I'm kind of saying there? All right. So why do we care about being able to make these models? Right? What would we want to use this model to do? Well, the big goal or the purpose of making models is to be able to make a prediction, right? We've measured some data. Can we make a prediction about, like, you know, the weight when the length is, say, like, I don't know, 58 or something? So let's do that for each of these 4 models we've created and just kind of get an idea of what's what each one of these would be. Okay. All right. So remember we stored 58 in the Y1 slot, right? Or I'm sorry, we stored the exponential equation in the Y1 slot. Everybody remember that? So what I'm going to do is I'm just going to press vars, go over to Y vars, select function and Y1. and just do y1 of 58. So 2707. And what do we put? We put y2 was our next one. So there we have 3378. And then the cubic was in y3. So 34.04. Notice that surprisingly, the model there, the logarithmic that had a really bad, well, had the worst r squared, so far is actually the closest to the one with the best r squared as far as the predictions go. And then our last model we did was this power one here at the end. And when we do that, we get 30.25. So again, depending on the model, we're getting a variety of different predictions. Everybody's okay with that? What could be going on that would make, well, let me ask this question. Are these which one of these predictions you think, which one is the most reliable, would you say? The cubic one, probably, right? Why? It's the one that most closely fit the data that we had the highest r squared value. That's true under certain circumstances. Why is this particular prediction fairly reliable? The value that we're asking for a prediction from is inside the range of values that we built our model from, right? 58 is kind of in between 12 and 72. If we had done the same thing with 1,000, I'm not going to write these down. We'll just kind of look at what that comes up on our calculator, which is way outside of the range of values we used to build our model with, right? Let's see what we get if we had changed these to 1,000. So the exponential, I get 3.18 times 10 to the 40th. That seems patently absurd. An organism that's 1,000 units long that has 3 times 10 to 20 to 3 times 18 to the 40th times 10 to the 40th. Woo! It's a big stinking animal. Let's do the logarithmic. There, it's 115. It seems a bit small to me, but considering 72 was less than half of that. Let's see what the cubic gives us. Well, that's plainly absurd, right? You're not going to get negative weight. Let's see what the power does. That might be the most realistic of our estimates there, somehow surprisingly. What do you think? Now, why were these values, like, why were these predictions so all over the place as compared to when we did W of 58, where these were, in comparison, much more closely grouped together? Well, this is a quirk of almost all predictions. So let's make some notes of this. So the first type of prediction we have is interpolation. That's where the prediction, well, let's just say predicting for a value inside the extremes of the data set. And then the other is extrapolation. This is where we're predicting for values outside of the extremes of the data sets. So just to be clear, when we did W of 58, that was an example of interpolation, and when we did the W of 1000, that was an example of extrapolation. And maybe I'm going to actually move this heading down here, and we'll just, oh boise, how did I miss some stuff? We'll just call this types of prediction. Okay. That's maybe a little bit better. Everybody cool as to what constitutes interpolation and extrapolation? Fairly easy to understand, right? And why extrapolation tends to things go wrong is the prime example is this cubic function, right? We pick this cubic function, it fits the data set that we have really well, but if you add some context to the real world, it's like, why the heck would the organisms, like weight be a cubic function? And we actually try to use the cubic function to model a big organism, you get a negative value for the weight, which is like patently absurd. You know what I mean? So one reason why you have a bad prediction is you're trying to do extrapolation. Is extrapolation always going to be bad? No, not always. When would you expect extrapolation to be the most reasonable? No, it doesn't really depend on the model. It depends on how far past the end of your data set you're talking about. So if we did the same thing, except we were looking at like the W of 75, there I would suspect we'd get much more reasonable values and things that were much more reasonably close together. right? Remember our data set ended at 72, I believe. Now the log one is a poor example there, which is clearly kind of absurd because it's lighter now than the 72 length organism. And the 3, which one was the 3? The cubic, which was pretty good, right? And then if we do the last one we did had was the power. Which is also like not maybe unreasonable, though maybe a little high. But these are all like, you know, not crazy values. Those are much more closely grouped together than when we looked at W of 1,000, right? And maybe if you have a really good model, some extrapolation near the edge might still be okay. But where you get into trouble is when you start extrapolating really far out past the end of your data set. Now, there's a prediction that probably all of us look at probably almost every day. There's a great example of this. Anybody know what I'm talking about? The weather, right? You look at the weather forecast. The weather forecast for the next hour, probably pretty reliable. The next day, still pretty good. Maybe the 10-day, it's all right. But you start going like, what's the weather going to be like next year? You know, you can you can be very wrong there. You know what I mean? Especially if you're trying to talk about precipitation. Like, is it going to rain next year on this date? Roll the dice on that one, my man. Nobody's got any. You can't do a good job of predicting that at all. You know what I mean? Does that make sense? And we've all experienced that, right? Like, what's going to happen? What's the weather going to be like in the next hour? You can count on that when you look at your weather app. You know, the next 3 hours, you know, probably still, you know, tomorrow, you know, like pretty reliable. But you go like to the end of the 10-day and it's like, I'm not really sure. I think it's going to be 96 on Sunday or something, you know, like 10 days from now. I don't know if it's not actually the weather. I just was picking a number. Don't panic. Yeah. Okay. So extrapolation can be one reason why a prediction fails. What's another reason? What might be another reason you made a bad a prediction goes wrong? Well, suppose we chose the logarithmic option and we use that to make our predictions. Would that be a good idea? No, right? Why? The r squared value wasn't a good fit. The r squared value was kind of far from 1. So we just had to we picked the wrong model. You know, you just don't have a great model for it. Does that feel okay? Make sense there, right? We saw that even the log model could be kind of bad, even when you're doing interpolation. What else? What else could cause a prediction to go wrong? Yeah.
Major outlier.
Yeah, so we're going to make a category called bad data. So one of those could be like outliers, sure. What else could be wrong with your data set?
Be limited to.
Too few.
Yeah.
Too few measurements, sure. Now, in general, how many measurements would you like? All of them, infinitely many, right? All possible measurements would be nice. Is that realistic? No. But typically more is better. All right, sure. There's another one that's a little bit more subtle than this. Let me give you this scenario. Suppose Mr. Kulik was trying to make a model that uses age to predict height. Okay? And I go over to the elementary school and I make all my measurements at the elementary school. You think that's going to turn out to be very good? Probably not. Why not?
Oh, and the data sets in the same area.
But why is that a problem for this particular instance?
Not getting the widest set that you can get.
When are you growing the most?
After that.
Probably when you're a little kid, right? You can almost double in height from like first grade to sixth grade. Yeah. So using that model, maybe at age 40, you're going to be 75 feet tall. You know what I mean? So what I would describe this as just like bias data. Or if I did the same thing, but I took a nice sampling of all ages, but I only took them from men. And men that played organized basketball, so are probably taller than average. Is that going to give us good predictions? No, right? Particularly if you picked women or tried to predict a woman's height, who on average are what, like 6 inches shorter than men, I think is the average. Is that right? 4 inches, something like that. So you get the idea there with the bias data. Anybody have another idea? I don't think of nothing comes to my mind right now, but those are I think are all the classical examples. One of the most famous bad predictions led to, you guys remember that big housing related stock market crash from, 10 years ago or something? Is that vaguely, I know you were young then. The Big Short thing? Does it ring a bell? Maybe. This is a classical example of extrapolation gone wrong, that the models they were creating, you're getting activity levels outside of the boundaries of their model, and the models didn't know how to handle them, so they didn't properly assess the amount of risk that they were taking on. There's a lot of other things going on there too, but a lot of other failures in the system. But that was a big one, is that just we weren't assessing risk correctly because the market conditions were outside of the conditions in their models to handle their risk assessment tools. All right. So that's kind of the gist of Chapter 12. You're just going to be getting these data sets. You're going to be building these models, going to be making predictions with their models and then assessing whether that prediction is reliable or not. So overall, the calculator does all the heavy lifting for you, right? Your job is just like using your noodle to decide like, which model should I use? Is this a good model? Make a prediction with the model. Is this a good prediction? Is it a bad prediction? Can I count on this? It's just doing that kind of stuff. Does that feel okay, guys? Okay. We'll stop here. I would strongly encourage you guys, though, that to do some of the 22 problem set or chapter 12 problem set, even if it's just like typing the stuff into your calculator and making sure you can do the calculator parts of it, because it's not, a lot of these cases, there's nothing really to write down. You're just putting the putting the data in, pulling a model out, making a prediction with it, and you're done, kind of thing. But I would make sure that I've practiced with that, so I'm capable, comfortable using my calculator to do those sorts of things. Particularly if you didn't have your calculator with you today, or you weren't following along while we were doing this. So you've at least like run through those steps, so you can like enter data in and make a scatter plot and generate a regression equation and do the like prediction piece and But in general, it's the calculator handles all the complicated stuff. And I'm not even going to talk about how the calculator is handling the complicated stuff because it's beyond the scope of what we need to do right now. It's not that complicated, but it is. It's more complicated than we have time for. Let me put it that way. In Mr. Kulik's day, we talked about how to do all this stuff by hand, which was just a lot of fun. Or at least how to do like approximations of these things by hand, which again, like a lot of fun. All right, I'm gonna stop.